The common trend I see with all these digital transformations is that we are going away from a world where we reduce the complexity to a world where we live on top of those complexity. And so we see this with how organizations are reinventing. We see that with new technologies emerging. We see that with cultural change. And to emphasize a little bit, let me again make the case about artificial intelligence versus platforms. So on the one hand, you take intelligence, you put it into an algorithm, and you can create complex automation. On the other hand, you take the intelligence, you put it into a platform, and you can create complex coordination. So this is something more interested for the transformation of organizations, where coordination is an essential aspect. But in both cases, it is about doing something with complexity. So it's complex automation or it's complex coordination. So the central theme here is complexity. And what I want to emphasize in this video is that to deal with complexity, and that's the world is becoming more complex, we need to go beyond design thinking. So design thinking was good if we would need to understand the system you are part of. For example, you are part of your family, right? So that's a system way of thinking, and design thinking helps you in understanding the parts in the system. What we now need to do with like the cybernetic way of thinking is understanding the flows where in that system, where it allows to amplify one thing and damp another thing. So those things like amplifications and perturbations and feedbacks and those structures, how do we start thinking like that? Okay, so I ended last video with a picture showing like design thinking is pretty old, and we've moved, definitely in academical sense, moved far away from this. I can use artistic feelings, because when the scientist is actually allowing us to see beyond what we are normal to we find normal to see, but the artist is capable of doing that with a gut feeling. Okay, you can't see my gut feeling. So what I like there is that the scientists, there's only small peers who can validate and fully understand it. You see that a lot of the essential aspects get lost in translation. So I will show that also in this video. And to move to this cybernetic way of thinking. So this transition, I think, is essential and relates to what I mentioned in the last part of the previous video around IQ tests, and I'm not going to go again into detail about that. But the essence is that a century ago, our grandparents were the way they were thinking was concrete and local. What has changed over a century is that today we take the hypothetical serious. So that's okay. People can imagine and take a hypothesis serious, that it's possible. But what is still very hard for most is understanding the flow that this hypothesis will create, and therefore not capable of seeing like, okay, so if you implement it in a complex adaptive environment, what starts moving all the way. So, okay. To start, I want to talk about concept of feedback, feed forward, so how the similarity in patterns emerge. And I think from an artistic point of view and from a zeitgeist perspective, these Russian dolls are a very good visualization of what it means, because it means not just that things can have similar patterns when they go bigger or smaller, but space starts getting a whole new dimension. You see, these dolls can be nested in each other. So there's like this onion layer, and that relates well again to also what we saw with reinventing innovation in organizations. Okay, so I want to emphasize a little bit more this self-similarity, and I will do that with concepts that will become more important later on as well. which relate to fractals. But before getting to fractals, you will see that again, from a scientific point of view, what we see as this self-similarity and what we understand as fractals are a little bit different. I'm going to introduce this now just to see the self-similarities, how these patterns reappear and what that means.
Who doesn't like fractals? They're a beautiful blend of simplicity and complexity, often including these infinitely repeating patterns. Programmers in particular tend to be especially fond of them because it takes a shockingly small amount of code to produce images that are way more intricate than any human hand ever could hope to draw. But a lot of people don't actually know the definition of a fractal, at least not the one that Benoit Mandelbrot, the father of fractal geometry, had in mind. A common misconception is that fractals are shapes that are perfectly self-similar. For example, this snowflake-looking shape right here, called the Van Koch snowflake, consists of 3 different segments. And each one of these is perfectly self-similar, in that when you zoom in on it, you get a perfectly identical copy of the original. Likewise, the famous Sierpinski triangle consists of 3 smaller, identical copies of itself. And don't get me wrong, self-similar shapes are definitely beautiful, and they're a good toy model for what fractals really are. But Mandelbrot had a much broader conception in mind, one motivated not by beauty, but more by a pragmatic desire to model nature in a way that actually captures roughness. In some ways, fractal geometry is a rebellion against calculus, whose central assumption is that things tend to look smooth if you zoom in far enough. But Mandelbrot saw this as overly idealized, or at least needlessly idealized, resulting in models that neglect the finer details of the thing that they're actually modeling.
An interesting aspect here is that oversimplifying what you are modeling is pretty central, and that's basically very common in a design thinking way. It's about being lean, about making things smooth and simple, and so that's the not rough part of way of thinking. Why isn't that working anymore? The reason to fully understand that, you need to go into chaos theory and the origin of this complex adaptive systems insights, and it is all to do with this feedback and feed forward, because things are changing in a way that we don't fully have grip on. And the classical example they give is the butterfly effect. So the idea is that a butterfly on one side of the ocean can become a hurricane on the other side of an ocean. Now that's again a very oversimplified idea. The whole idea is that there are these effects, feedback effects, positive feedback, negative feedback, and all kind of complex interactions, flows that make that something that could be neglected in one setting suddenly becomes essential in another setting. And notice that I've focused on construction, and this concept of these feedback structures in construction are pretty well known, like when they were building bridges that would collapse because of a resonance in the wind, or because military would go in cadence over it. That's kind of this amplification factor that we are investigating. And in a society and organizations and business and all this environment around us, we see that this closer connectivity with everything makes that this chaos theory concepts are becoming central. So we are gaining increasingly a need to deal with this roughness, with these details that can change things. Now, where do we know this best? Well, of course, in weather forecast. So if you think about weather forecast, you can only very accurately predict a week or 2 weeks, but to do more, you need these good models of how all this complex adaptive environment is changing. So to predict the weather, we create simulations. So we created this simulated worldview, and that's where I want to get into, call it simulated. I mean, if you look at the description, I called it artificial life thinking. So, okay, what's in the name? I don't care, as long as you understand that it is about these flow structures, including these flow structures. Now, Okay, so if I look at the list I have of the different ways of thinking, you see that one of the next levels of thinking after system thinking is this the digital thinking. And digital, of course, we know it as zeros and ones, but there are many ways to see digital around us in our environment. I mean, if you ask me what is the first radical digital transformation, I would say the alphabet. We moved from describing a language in a more concrete way to describing the language in a more abstract way. So that's again from that concrete thinking to that abstract thinking. So and what we can actually see is that this the use of digital can be a very useful tool to measure roughness, because you approximate values instead of that you really tackle the values. And I'll go again to the video of the fractals to show you how we do that.
Cover the plane with a grid and highlight all of the grid squares that are touching the disk. And now count how many there are. In the back of our minds, we already know that a disk is two-dimensional, and the number of grid squares that it touches should be proportional to its area. A clever way to verify this empirically is to scale up that disk by some factor, like 2, and count how many grid squares touch this new scaled-up version. What you should find is that that number has increased approximately in proportion to the square of our scaling factor, which in this case means about 4 times as many boxes. Well, admittedly what's on the screen here might not look that convincing, but it's just because the grid is really coarse. If instead you took a much finer grid, one that more tightly captures the intent we're going for here by measuring the size of the circle, that relationship of quadrupling the number of boxes touched when you scale the disk by a factor of 2 should shine through more clearly. I'll admit though that when I was animating this, I was surprised by just how slowly this value converges to 4.
The essential aspect I want to emphasize here is by going digital, we can approximate what we're trying to get. Now, if you think about the alphabet, it was enough to get 26 characters and have a good model and so on. But if you see over here, they show that to actually use this box counting as a way of measuring, you need a lot of counting going on. And this problem that it goes so slowly to the value you want to get to will actually be very important if you think about approaching that roughness of the fractal, but very concrete to artificial intelligence. You see that many of these algorithms were more or less in place a few decades ago, but the fact that we now actually are capable of having these huge data farms capable of doing extremely many computations is why the AI is catching up, getting close enough to what we want to achieve, namely be as good as visual recognition as humans, for example. So that's why now it is becoming an issue, because only now we have the computing power to do that, but from the models, they are old.
Now, getting back to fractals, let's play this game with the Sierpinski triangle, counting how many boxes are touching points in that shape. How would you imagine that number compares to scaling up the triangle by a factor of 2 and counting the new number of boxes touched? Well, the proportion of boxes touched by the big one to the number of boxes touched by the small one should be about 3. After all, that bigger version is just built up of 3 copies of the smaller version. But importantly, the whole reason that I'm talking about this is that we can play the same game with non-self-similar shapes that still have some kind of roughness. And the classic example here is the coastline of Britain. If you plop that coastline into the plane and count how many boxes are touching it, and then scale it by some amount, and count how many boxes are touching that new scaled version, what you'd find is that the number of boxes touching the coastline increases approximately in proportion to the scaling factor raised to the power of 1.21. Here, it's
far I've looked at self-similarity and digital thinking. So let me go back to the list of the ways of thinking within construction, and you need to be careful here because very often the pragmatic need to construct something made these people create the way of thinking. So it was the way of thinking didn't exist at that time. For example, the second one, the system way of thinking, you could see them in the construction, in many of the construction around the first industrial revolution, and definitely in the second industrial revolution. But it wasn't that these engineers had this system thinking as a mindset. I mean, system thinking as a research will come up in 1930s, and you will see that it will be related to another kind of construction happening at that time, and that's the code thinking. So that's where I'm gonna focus at Gödel. Now, if I think about why do I pinpoint the digital thinking to Morse? Because first of all, of course, we know the Morse codes, but the whole interconnectivity, thanks to that new kind of technology, changed the world in a way that it became more of this interconnected world where all these amplifications and perturbation effects could appear. And it looks like it has played a very important role for the events of past century. Okay, I'm not gonna go into detail to that. I'm not an expert in the First and Second World War, but it sounds remarkable how related that communication technology and mobilization technology has played a role in all these escalating events. And I see all these escalating events exactly as this butterfly effect. So this kind of escalated on itself in the development and thinking as well. And that's where we come to Gödel and things like the halting problem, where it was a mathematical, logical problem at first, but then it also becomes used for, it's related to calculations and electronic development around that time, leading eventually to our computers. But you see here a situation where there's such a big cycle that the whole thing can actually be reinvented by the thing itself. And I think a very good illustration of that is given by Escher with the hand drawing the hand. And I like this visualization of it because you see the hand drawing the other hand. And then just wiping it out again and drawing again. And basically, if you look at global social events a century ago, that's what people were doing. They were just throwing out the existing social structures and reinventing new ones, while we have learned that there are some, we've learned it's dangerous because basically you don't fully understand all this perturbations and changes. So let me make a bold claim and say that code thinking is creating mental models. And it is about taking the virtual serious, so not just taking the hypothetical serious, like A can be B, but actually understand that the virtual is an entity on itself that can start creating action in the world. And that's basically where you see cognitive models coming in. You see that around that time, it is a seed for all these artificial intelligence models. And if you go back to what I started with, saying that you can have AI and that allows you to automate complexity, or you can take platforms and that allows you to coordinate complexity. In both cases, it is this software, this code thinking, that makes complexity approachable, while before the complexity was cut down in more restricted, simplified things. that we could deal with. But because of this amplification, that's not possible anymore. So we need to move to cognitive models. We basically need intelligence in everything, right? And so that's where we're going to move towards. And what you see in those models is that you can create all kind of models. And if you think about many different programming languages like object-oriented, logical programming, can't get to all of them, coding in more of them than I can think of. The essence is that all of them allows a other way to express whatever you're trying to do. And there's this whole concept of a balance that needs to be maintained. And that's the thing I'm going to go back to, while at the same time going a little bit deeper into fractal thinking, because that's something we didn't address yet. So I'll talk about both the balance and the fractal thinking. Well, I'll show you a video.
What he observed is that self-similar shapes give a basis for modeling the regularity in some forms of roughness. But the popular perception that fractals only include perfectly self-similar shapes is another over-idealization, one that ironically goes against the pragmatic spirit of fractal geometry's origins. The real definition of fractals has to do with this idea of fractal dimension, the main topic of this video. You see, there is a certain way to define the word dimension in which the Sierpinski triangle is approximately 1.585 dimensional, that the von Koch curve is approximately 1.262 dimensional. The coastline of Britain turns out to be around 1.21 dimensional, and in general, it's possible to have shapes whose dimension is any positive real number, not just whole numbers. I really do think that this is one of those ideas where once you learn it, it makes you start looking at the world completely differently. What this number is, what this fractional dimension gives us, is a quantitative way to describe roughness. For example, the coastline of Norway is about 1.52 dimensional, which is a numerical way to communicate the fact that it's way more jaggedy than Britain's coastline. The surface of a calm ocean might have a fractal dimension only barely above 2, while a stormy one might have a dimension closer to 2.3.
So what this fractal thinking is illustrating us is that even in something as seemingly as simple as measurement, things become relative. And of course, this fits a zeitgeist. We've also seen a lot of relativity theory in physics. But I like to bring this back to reinventing organizations, the whole digital transformations, particularly the use of artificial intelligence and in platforms. And in both cases, what you see is you need to include that relativity part. In both cases, I start like you take intelligence, meaning that intelligence exists independent of it, but you can aggregate some very interesting features for it. And that's very related to this integer versions of dimensions, right? It's the essence is it's not like, okay, it is fully automated. No, you can question is like 1.5 automation. So in all these aspects, you're going to do an aggregation of that intelligence and start dealing with that complexity. And I must say that thinking in these relative terms is still a very challenging way to do in this time period. I mean, think about quantum physics is definitely challenging us, like being a particle and particle duality, particle wave duality. But in the same time, you can start wondering if our consciousness and our intelligence isn't a particle wave duality. Aren't we at the same time an individual and at the same time part of a culture? And with all these things about collective unconsciousness, those parts of archetypes showing us that how influential this culture is. Notice also about the difference between concrete thinking, analytical thinking, and this more modern ways of thinking, how that actually affect your IQ rating. So all these things are we need to try and move to new ways of thinking that are capable of dealing with the complexity around us. And that way of thinking is cybernetic thinking. Basically, it means that like what we are doing with our sensory input is we are constantly getting input, and we don't see the objects exactly. We make models of those objects, because I mean, if you go to many of the things like in change blindness, they will demonstrate you that the things you are perceiving may not always be the things that are actually there. So that's the thing, is what we are doing is taking a loop with all the sensories coming into us to create models, that's that virtual world that we accept as our reality. And it's in that interplay, in that kind of thinking, in mental models, that needs to start happening basically everywhere. I mean, if I look at an organization, I see it from a fractal point. I see it as a simulated structure where we can create these weather forecasting models to actually start in creating a whole flow and a whole, so the consciousness of that organization. And again, that consciousness of that organization won't be absolute. It would be an aggregation of all of the parts in it. And that kind of thinking is going to be more needed if we want to understand artificial intelligence, and for example why it leads to ethical debates, which was previous video. And I hope it can actually also help to start explaining why the scaled frameworks, agile frameworks, are costly and inefficient. And I'll going probably back to that topic next week if there's nothing else coming my way to respond to. And so maybe you can actually be one of those effects. Maybe a good question or a request could lead to a specific video. So please subscribe. Hope to see you again. If you have any questions, contact me.